The lemma above, namely the Chang-Erdős inequality, will imply the following theorem. Due to Kochen and Stone, let omega A and P be a probability space and let A sub n, where n is a positive integer, be such that the summation of the probability of those events is equal to infinity. Now we are not assuming that A sub n's are independent. But without that assumption, we still have the following inequality. That the events A sub n happening infinite often, meaning that the lim superset of A sub n's has a probability greater or equal to the lim sup as n goes to infinity of the following quotient. In the numerator, you get the summation from k equal to 1 to n of p of A sub k's, and you square this sum. And in the denominator, you're going to get this double sum from ik equal to 1 to n of the probability of the intersection ai intersection A sub k. And meanwhile, this guy is same as the following lim sup. The lim sup of the quotient of two partial sums. In the numerator, you get the summation of all those p of ai times p of ak, where I is strictly less than k, ranging from 1 to n. And in the denominator, so this summation is still over the upper triangular part of this double indexed of this matrix of two indices. The summation of p of ai intersection ak. First, I would like to point out that this theorem is really a generalization of the Borel Cantelli lemma, or the converse of the Borel Cantelli. So, the Kochen Stone theorem implies the Borel Cantelli lemma. That is because if the events A sub n's are pairwise independent. Or more generally, just negatively correlated. By this we mean that the probability of the intersection is less than or equal to the product of the probability for any I not equal to k. When those two cases happens, you know that the denominator will be less than or equal to the numerator. If they are pairwise independent, then they are actually the same. If they are negatively correlated, then by definition, the denominator is less than or equal to the numerator. Anyway, this implies that the probability of A sub n happening infinitely often will be greater or equal to 1. But the probability of the whole space is 1. So, the probability of A sub n happening infinitely often is equal to 1. So this is really a generalization of Borel Cantelli lemma. Now, let's give a proof. For reference, let me copy both the Chang-Erdős inequality and Kochen Stone theorem down in here. So now let's prove this theorem. This proof is due to the Professor Yan in the Chinese Academy of Sciences. The basic idea is the following. We'll first consider only finite many terms so that we could apply this inequality, and then we'll take the limit. Somehow, we need to use this condition. Actually, in the end, we are not dealing with limit directly. We'll play with the limit of some other quotients, which turns out to have the same limit as those quotients. And that is where we're going to use the sum of those probabilities is equal to infinity. So let's get started. Let A sub n to be equal to the summation from k equal to 1 to n of those probabilities of A sub case squared, and let B sub n to be the double sum from ik equal to 1 to n of the probability of the product events or the intersection of two events ai and ak. Now, by hypothesis that the summation of those probabilities is equal to infinity, you know that A sub n will go to infinity as n goes to infinity. So, by using the Chang-Erdős inequality, we have that B sub n is greater or equal to A sub n divided by the probability of the union of those events. But you know that the denominator is bounded by 1, So this guy will be greater or equal to a sub n, which goes to infinity as n goes to infinity. So b sub n will also go to infinity. Remember, our goal is to study the probability of this lim sup set. And the lim sup, by definition, is the intersection of the union, where k is from m plus 1 to infinity, of a sub k, and the intersection is taken from m equal to 1 to infinity. This is a little complicated, but we are going to focus only on this part. You look at the probability of this tail union. This guy is equal to the limit of this truncated union by the properties of the probability measure. And this, if you just look at this part, and you apply the Chong-Erdős inequality again to this part, what you get is the following. In the numerator, you get the square of the summation from k equal to m plus 1 to n of the probabilities of a subcase. And in the denominator, you're going to get this double sum ik from m plus 1 to n of the probability of the product events. Now, when you take the limit, although you know the limit of this guy always exists, because this is a monotone term, you do not know whether the limit of this quotient exists. So the best you can do at this moment is the lim sup. You know that this limit is greater or equal to the lim sup. Now, using the notation on the left, you can simplify this a little bit. The numerator will just be the square of the difference between square root of a sub n and the square root of a sub m by our definition of a sub n. And the denominator will be just b sub n minus b sub m. This lim sup can be further simplified by using the fact that limit of an is infinity and the limit of bn is also infinity. So now I would like you to think about it, how to simplify this, and I will tell the answer later. So if you compute the numerator, you'll get 3 parts. And the denominator is just bn minus bm. Because m is fixed, and both a sub n and b sub n will go to infinity, so the term that really dominates the limit will be those two guys. Because we know that a sub n is bounded about by b sub n, and the square root of a sub n will grow much slower than b sub n. So this guy will be nothing as n goes to infinity. We'll fix m. So this lim sup turns out to be equal to the lim sup as n goes to infinity of just an over bn. But an is precisely the numerator and bn is precisely the denominator of this first inequality we want to prove. Now you take m go to infinity. It follows that. So what happens if you take the limit as m go to infinity? You know that this left hand side will be equal to the probability of the intersection from m equal to 1 to infinity of the union from k equal to m plus 1 to infinity of a sub case. And by the inequality that we just derived, the left hand side is bigger or equal to the lim sup of this quotient. But this quotient a over bn is just this. That is how we define a sub n and b sub n. A sub n is this numerator and b sub n is this denominator. So this proves the first inequality. Now let's look at why this lim sup is same as this lim sup. Now let's check this. The first observation is that you should have noticed that this partial sum is part of this, and this partial sum is part of this. Specifically, you should have noticed that the square of this sum is equal to the twice of this numerator plus the sum of the squares of probability of a subcase. And this sum is equal to the twice of the sum of probabilities where I is less than k, plus the sum of probabilities of a subcase. What we want to do now, in order to show that when it takes a lim sup, the both sides, the left hand side is equal to the right hand side, is that we want to show that the part in this red box is negligible compared with the part in the blue box as n goes to infinity. To this end, we are going to give a lower bound and upper bound of this, which turns out all equal to the guy in the blue box as n goes to infinity. In fact, this quotient is squeezed between the quotient will ignore this part. So this is bigger or equal to this. And at the same time, it is less than or equal to the quotient will ignore this part. So now let's look at this lower bound and upper bound separately. This lower bound, if you divide both the numerator and denominator by this guy, this numerator will be equal to 1 over the reciprocal of the guy in the blue box plus this red underlined part divided by numerator. And this upper bound will be equal to the sum of those two terms. So just split this. Now, in order to show that the guy in the blue box will have the same lim sup with this guy, it suffices to show that those two green parts will go to 0 as n goes to infinity. If they both go to 0 as n goes to infinity, you know that those two parts will agree. This is just a reciprocal of this. And it follows that this guy and this part will have the same lim sup. Meanwhile, you should notice that because this numerator is always less than or equal to this, because the probability is always bounded by 1, it suffices to show that this guy will converge to 0 as n goes to infinity. So now let's show that. So now we claim this limit is 0. To check this, we simply observe that the square of this guy, which is 2 times of this partial sum, plus the summation over the diagonal, namely the summation from k equal to 1 to n of the squared probabilities. And this is less than or equal to this guy plus the summation without the square. And now you divide both sides by this sum. And you get the summation from k to 1 to n of p of a sub k is less than or equal to the twice of the summation of p of ai times p of ak divided by the sum plus what? But you know that the left hand side will go to infinity as n goes to infinity. That is our hypothesis. The infinite sum from k equal to 1 to infinity of p of ak's is equal to infinity. It follows that this quotient must be infinity as n goes to infinity. So the reciprocal of this will go to 0 as n goes to infinity. And that verifies this claim. Since we have shown that those green parts will go to 0 as n goes to infinity, we have verified that this quotient will have the same lim sup with this quotient. 2 and 2 will cancel out, and the lim sup of this guy will be equal to the lim sup of this guy as n goes to infinity. Because this whole thing can be squeezed between those two things, which actually have the same limit due to the fact that the green part will go to 0 as n goes to infinity. And finally, we are done with this equality. And that is the end of the proof.